Okay, welcome back to the next session. In this session, we will learn about closed sets. So, to define closed sets, we will be, or to establish different definitions of closed sets, we will be needing a definition called closure of a set. So, to define closure of a set, before that, let me define what is an adherent point. So, a real number xi is said to be adherent point of a set S subset of R if every neighborhood of psi contains at least one point of S. Okay, so how is it different from limit point? So you have to think how adherent point is different from limit point. Okay, this is the question to think. So bulb. Okay. We will discuss or talk about all these bulbs and enlighten ourselves when we meet for the live sessions. And next definition is closure of a set. So it is defined as S and it is denoted as S overhead bar. It is called as S closure. Okay. So this is equal to S union L of S. That is the set union with its derived set. Okay. So that's the closure of a set. For example, so we defined what is the derived set of Q, that is set of all rationals. L of Q was R, right? So Q closure would be Q union R, correct? So that is nothing but R itself. Second, R closure is R union L of R. So that's R again. Okay. Third one, null set, which is very trivial. Null set is null set union derived set of null set is nothing but null set itself. So we define a closed set in many ways, and one such way is using closure of a set. So a set S is closed if each of its limit points is a member of itself, or member of itself. Okay, so or in other words, we can also say that a set is closed if it contains all its limit points. That is, if the closure of a set is the set itself. Okay, so we discussed about a closed interval in the previous video, where we found out that the derived set of the closed interval was the set itself, right? Because it contains all its limit points a and b, and every element in between a and b, every real number is a limit point. Is a limit point. So what would be the closure of the interval? So it is nothing but the interval union the derived set is nothing but the interval again, correct? So that is nothing but the interval itself. So from this, what can you conclude? You can conclude that every closed interval is a closed set. So there is a question in the homework list where someone has opted for that question, I think number 7 or something. So wherein you will have to show whether certain kind of sets are open or closed, or they are neither open nor closed kind of thing. So if you are asked to find out whether a set is closed or not, you just need to prove that it contains all its limit points. Another way to show a set is closed is using this definition. Okay, a set F in a metric space X comma D is closed if F complement F overhead C is equal to, which is nothing but M minus F or M mod F. Okay. M mod F is open. So its complement is open is another way to show a set is closed. I should have, this becomes a quotient space. I should have things like this. Okay. M mod F is open. So if the complement is open, the set is closed. Okay. So some examples of closed sets are, so from the above examples, we can definitely conclude that these two are closed sets because the closure is the set itself. Okay. So, and some more examples are, main set, if you are in a metric space X comma D, then X is both open and closed, correct? And same way null set is both open and closed. I'm sorry, I'm not just going back and re-recording for a sneeze. You'll have to deal with all this throughout this maybe this month because it's an allergy season. Okay, so an arbitrary intersection of closed set, an arbitrary intersection of closed sets is closed. So how is this? We know that finite intersection of open sets is open, right? So we know that finite intersection of open sets is open. So suppose if you take A alphas where each A alpha is open for each alpha, so then intersection alpha is equal to 1 to n, A alpha is open, correct, where n is some finite number. Okay. So now applying De Morgan's laws to them, what happens if I apply, then when this is open, this whole complement is closed, right? Complement is closed. But what happens to the whole complement? It is nothing but union alpha is equal to I to n A alpha complement by one of the De Morgan's laws, correct? So then this is closed. So similarly, to establish this above statement that I made here, arbitrary union of open sets is open. Okay, is open. So complement of that would be closed by definition. So that is nothing but by De Morgan's law, union becomes intersection. This is closed. But each A alpha was open here, right? Correct? So A alpha complement, each A alpha complement would be closed. So this is nothing but arbitrary intersection of closed sets is closed. So that's what we stated here. And this one here is resulting in finite union of, so I will number this 1, this 2. So 2 here implies this, correct? And 1 implies, what is that? Finite union of closed sets is closed. Okay, so what else? Okay, let me define an open ball to you, a representation. An open ball of radius, okay, an open ball of radius epsilon would be denoted as b epsilon of x, of radius epsilon and center x is denoted by this b epsilon of x, open braces, x, which is nothing but all those y belongs to set X, an open ball in a metric space. Okay, all definitions have to be precise. So all those y whose distance from x to y is less than epsilon. Okay, so it is nothing but center x and radius epsilon, that's the ball, and all the blue region are those points whose distance is less than epsilon, and the dotted lines aren't included, so it's an open ball. Okay, so then okay, another example for closed sets. Why did I define this here? You will know why did I do it. So another example for closed sets. This was a second example. Okay, so third example is any finite set is closed. Any finite set is closed. So why is that? And to prove this, it is enough if we show singleton set is closed. Singleton set is closed. Okay, so why it is enough if we show this? It's the bulb again. So let me see who can answer this. To show any finite set is closed, it is enough if we show that singleton set is closed. Okay, so this is the second bulb of this video. Think on this. Think why, and let me know why. Okay, yeah, to prove that singleton set is closed, so consider the metric space x comma d. Okay, and singleton set for any y belonging to x minus x, singleton set x, where y is not equal to x, what happens? Epsilon, which is equal to distance between x comma y, when they are not equal to each other, they will always be greater than 0 by definition of the metric, right? So we have this b epsilon of y, okay, b epsilon of y, the open ball, to be subset of x mod x. So what happens if an open ball is a subset of a set? So that is nothing but, if I consider this set to be x mod x, okay, so open ball for any random y, my y is arbitrary, so I can consider a random y, and you say that the open balls round those y's are subsets of this set itself. So then it means that this set here is a neighborhood of each of its points, right? So if it is a neighborhood of each of its points, by definition, what kind of a set does x mod singleton set x becomes? It becomes an open set. Therefore, the complement of it is nothing but singleton set is closed. So we proved that singleton sets are closed. So how does that imply any finite set is closed? Think on it, and it's pretty easy and you can answer. Okay, so then we have a next example, which is a part of your homework, I guess. So each of the intervals, closed interval a comma b, closed interval a comma infinity, or negative infinity comma b, is closed. And even natural numbers, set of all natural numbers, and Cantor's set denoted by delta. So this is nothing but Cantor's set. So read the book for this set and what kind of a set it is, and I will definitely introduce this set in when we discuss about countability. So this is also closed. So here comes your third bulb of the day, of the video. Okay, so why is Cantor set closed? Okay, so let us discuss this when we meet. And okay, and in a discrete space is every possible subset is an open set. So every possible subset will be the complement of an open set. Therefore every subset is closed in a discrete space. So fifth one, in a discrete space every subset is closed. Actually both closed and open. Okay, and there are sets which are neither open nor closed. Once it is not closed, it doesn't mean it is open, or once it is not open, it doesn't mean it's not closed. And complement does not imply negation. So complement is not negation. Something apart from it is complement. Okay, so if it is not closed, it doesn't mean it is open. If it is not open, it doesn't mean it is closed. So there are some sets called G delta and F sigma. You must have learned them in measure theory. So G delta and F sigma are neither closed nor open. Okay, like some of the G delta and F sigma sets, not every G delta and F sigma. Okay, okay. So one more thing, that is this semi-open and semi-closed intervals. So they are neither open nor closed. Okay, so you have lots of theorems to show all these things. I think this is a part of your homework. So that is, if your definition, you have to prove your definition, that is, in a metric space x comma d, f is closed, uh, f is closed implies complement of x, f, that is f complement, is open. I don't know, I don't remember exactly if it is a part of your homework or not. So to you, this is a definition in itself, and if you have to prove this, okay, if and only if, actually, so if you have to prove this, you will have to use the definition of limit points. Okay, fine. And then what else? Yeah, closed sets. I think we discussed lots of examples. Go back and learn what are Cantor sets. Okay. So to show a set, if to show a set is closed, you have to prove that it contains all its limit points or its complement is open. And to show a set, if it is open, you have to prove that its complement is closed or it is a neighborhood of each of its points. To show a set is neither open nor closed, you have to show that it is neither a neighborhood of each of its points, nor it contains all its limit points. Okay, so you have an example 10 and example 11 that you should go through in page 36. Okay, yeah, okay, I'm running short of battery here. Let me I think I have covered almost everything that's required for a closed set. Okay, yeah, so that is it. In the next video we will, okay, yeah, I have to state something else too. Yeah, I'll do that in the next video. Some properties of a derived set, I'll do that in the next video. So this is it for this video. Think on all the light bulbs so that you throw more light to it.